Hello and welcome to my video on SNES sprites. So today I'll be going through how to set up some sprites to use on the Super Nintendo, and I will also go through some of the various issues you might encounter trying to use them. So first let's get into some of the console's limitations and bits and pieces when it comes to sprites. So the Super Nintendo could have a maximum of 128 sprites, and with those 128 sprites you can choose from any two sizes to use. So you can't have any sizes that you like, so you have to pick two of them here. So I would say probably a useful combination would be 16 by 16 and 32 by 32. So you have to specify an area of memory where your tiles for your sprites will actually reside in video RAM. So you're limited to only a maximum of 512 tiles. And there's also a weird sort of way that the tiles have to be laid out in video RAM for the graphics chip, the PPU, to actually be able to pick up the tiles and draw them as per the sizes that you request. So each sprite can have up to 16 colours, although the first colour in every palette will be treated as a transparent colour. So in effect you have 15 colours really in each. You can have any of 8 different palettes to choose from. And you are, as your sprites will be built from tiles, you have to be careful how many are on the horizontal line at once, which is the same as all of the retro consoles. We limit to how many sprites can be on any horizontal line. So the way that the Super Nintendo does this is each image of the sprite consists of tile parts of 8 by 8. So for example, a 16 by 16 image would have 2 tiles going across horizontally. A 32 by 32 tile image would have 4 tiles going across, and a 64 by 64 tile image, pixel image, would have 8 going across. So you can only have 34 of those tile parts on any horizontal line. As the sprites can move outside of the visible display, you have to be careful to not have one of your sprites count as the visible parts on the screen, because that could cause that sprites to not draw. So that's something to be aware of there. So the sprites also have the ability to mirror the images left and right, or up and down, via attribute flags, and you can also change the priority for them drawing over background layers. So you could have a sprite be below one background layer but drawn above another. Each sprite in memory, in OAM memory, consists of 4 bytes which make up the various components. So all of the sprites, when they're activated, are considered to be drawn. So to hide them you have to position them off screen. So the easiest way to do that would be to position the X coordinate at 256, or 257 rather, and then the Y coordinate to 224, for NTSC screens or 240 for PAL screens. So this is the format for your palettes. So it takes a 16-bit number for the red, green and blue colours. So blue, green and red can be in the range of 0 to 31 using these bit flags here. So you can have a range of 32k of colours, which is 32768. So if we get on to how you should lay them out in VRAM. So one thing to consider when putting your tiles into memory is you have to tell listeners the memory block in VRAM where the tiles actually reside for the PPU to be able to actually work with them. So as in the other videos I've done, one thing to remember with working with memory addresses on the Super Nintendo is they're actually in words, not in bytes. So for example, if you were using this memory address here to put your tiles, obviously in reality referring to that memory address in bytes, it would be 2000. But as we have to refer to it in words, it would actually be at 1000. So a word is 2 bytes. So I'll now get on to how you would lay out and how best to think of the tiles when you're trying to display them. So in this mock-up here, what this actually is supposed to be is an area of VRAM organized in pages. So you can think of a page as like a block of 256 bytes, which is one of the key things to work with when you're dealing with the tiles in video RAM. For example, all of the tiles have to be organized in a certain fashion. So for example, these represent individual tiles here. So this would be an 8x8 pixel tile. So in one page of 256 bytes, you would get 32 of these tiles, 0 to 31 being the bottom right here. Now, when you put these larger images into VRAM, they will span multiple pages, and you have to organize your images as such when you load them in. Otherwise, they will not be displayed properly. So you'll notice here, so I've kind of tried to create like a divide and grid here. So you can see these divided into pages here. So you have to be careful where you actually place the frames of your images as well. So this is a 32 by 32 pixel frame here. So you could not put it at this location above here. If you move this up to here and then you tried to draw this frame here, it wouldn't display right. So you need to align them correctly as you go along and load them in. It will make more sense when I kind of show it in show the example program in the emulator in a bit. So one thing to note is you can only have 4 32 by 32 pixel images on any one of these lines here. So if this block here was up here, then tile 0 would pick up your first Mario sprite. Then your next one would actually be at tile 4, would be where your next one is, because that would be like the top left there. Then that would be 8, and then that would be 12, because everything is actually split into 8 by 8 tiles. And then to draw the individual frames, you then have to be aware of where they actually reside, which can be fine to start off with on your first line. But then if they extend down here, so if you had more animation frames where the turtle bird things are, then this next frame here would be 64. So as you can see, the first frame 0, and then the second frame would be 64, which is quite a jump. And then if you had this 64 by 64 image here, again you have to be careful where you arrange these because of where the PPU expects to find them. And also, if you're working with really large images like the 64 by 64 size there, then you can only fit 8 of those into VRAM for your sprites. Likewise, the 32 by 32 pixel images, you can only fit 32 of those into VRAM at any one time. If you're working with 16 by 16 pixel tiles, then you can have up to 128 of them. So another thing to consider here with the bigger images is look at all this blank space around this image here. So when you have like an image frame, there's loads of like wasted space around. So if you do need to sort of draw a large character like this, then it might make sense to split it into smaller segments and then draw only using visible sort of blocks. So arrange it as like a jigsaw piece, and then say if you were making this from 16 by 16 bit pixel tiles, then you would be able to get rid of all of the wasted sort of empty space here, which would allow for extra sprites to be in VRAM. So you can mix the positions of some of these frames, but you have to make sure that they are aligned correctly to these certain like page areas. This won't make any sense until you actually play around with loading sprites in, by the way, or unless you've worked with the Super Nintendo before. So I'll stop going through this now and I'll actually show the demo program. Maybe that'll work. That'll make some more sense, hopefully. So first off, I'll show you some of the characters that we'll be seeing here. So we've got my angry chicken character here, and then this other pigeon character here. Those are some 64 by 64 pixel images for us. And then to round it off, we have some frames of Mario and the turtle bird thing. I did have a load more 32 by 32 pixel sprites I was going to show off, but I run out of VRAM. So I decided just to go with Mario and the turtle bird. So here we go, where they are running around. So we're using mode 1 for the background. I didn't play around with any of the priorities. Initially I was going to show you the priorities by changing some of the different flags, but due to time constraints I'm not going to be able to do that. So as you one of the things to bear in mind as well is when sprites move out the bottom of the screen here, as the Y coordinate for sprites for each sprite is only 256, 0 to 255 range, the graphics will wrap around at the top there. So if you're working with large 64 by 64 sprites, be careful if you have to try and scroll the screen, as they are likely to, or rather if you move them off of the bottom of the screen or the top of the screen, they will wrap around. Won't be showing it now, but you can play around with that and get that happening. So if we go into the tile viewer, now you'll see here that they've done all this here. So you've got a maximum of 16 tiles here. So this is the a font set here. Everything's using 16 color mode, or rather 4 bits per pixel tiles. And then you'll see that there's a 16 going across by 16 down. Now if we scroll down to our sprites here, and then if I select the color palette 8 here, so this is how they're laid out in VRAM, just like I was saying. So you can only have 2 64 by 64 sprites next to each other in VRAM like this. So when you draw them, literally when you draw in sprites, it's best to keep to a width of 128 pixels wide. That way when you load them into VRAM, they will be arranged correctly as you expect to see them. If you split them into smaller sizes, then you'll need to know the exact offset from where you've set tile memory for them. So if I cycle through the palettes here, you see the pigeon character uses palette 9, and then if we scroll down you'll see Mario and the turtle dove uses palette 10. And then you'll see how these are laid out here. So this is a very useful tool here when you're loading in graphics. It allows you to see exactly where you're putting them to make sure that they are at the location you expect them to be. So with that out of the way, I will now jump into the code and show you the Sprite Manager modules for working with sprites here. So there's a lot of convenience functions I've put in here. So the program itself isn't that big. I'm just using the title screen code here. We've got like a timer to switch the animations up. And there's a kind of nothing really sort of special going on here. This isn't really needed. This was what I was using for debugging. So one thing to be aware of as well is when you come to load in the tile data, whether that's for sprites or for your main sort of game, sometimes if you try and load in too much in one go, the console just chokes and dies, and then you end up with a load of garbage on screen where you expect your sprite data or your tiles to appear is just a load of rubbish because it hasn't been able, the console hasn't been able to get all of the stuff done before the vertical sync. So if you're experiencing glitchy tile data, you might need to try and break up the amount of tile data you're loading in at any one time. It's just a bit of info there. Can be frustrating to get around that, but that's part and parcel of working with the Super Nintendo, unfortunately. So some weird things when it comes to the Super Nintendo is so you have like a block of part of the sprite data in a list of 512 bytes, and then you have another 32 bytes positioned elsewhere with various bit flags which affect other parts of the sprites. Thankfully, PVSNESlib takes care of lots of this for us here, but it is good to be aware of what's actually going on here. So some of these bits here, these are convenience constants here for working with sprite attributes. So because they're the sprite attributes, you've got a kind of like a bit flag for mirroring the sprite horizontally, another one for vertically, and then you've got 3 different bit flag combinations to generate the priority for drawing above or below background layers. And then you've got another 7 here for your palette. There's also a bit flag here, so these are the actual bit flags here. So some of these are needed to work out the attribute byte value. So they're arranged in a weird way. So you've got 7 palettes here. So I would have thought it would have made sense to have these arranged at the very bottom of the bit flags, but for some reason that's not the case. So one of the first bytes here takes the tile number, so that would mean that you can only have a range between 0 and 255. So to be able to access all 512 possible tile locations for your sprite, 1 bit flag was moved and set aside in another attribute byte, which is why this bit flag here has to be set if you have a tile number which is greater than 255, which is why the this attribute function here handles all of this for us. So this one here is just the core bits, if you like, palette, priority, and flip X and Y. But then this doesn't handle if your sprite ID is greater than 255. And then I put in hide positions here. As I said, the as is also stated on there's wiki, the when you enable sprites, they're always, all of them are drawn, but to initialize them you have to put them off the screen so that they're hidden from display. So when I want to hide them using well, you can use this, but one of the convenient things I've created here is like a sprite batch system, which is basically an array of this struct here, which allows working with sprites to be a lot more simpler. So you have to decide what sizes they're going to be. So SNESlib has a number of I'll show you here, for example, these parameters here dictate what size combo you can actually work with. So if you're using this code for your own project, then be aware that this define here is set to 32 by 64 for this demo. So if you are using it for your own project, then you'll need to change this size here. And I've also limited the amount of these structs that we work with in this demo here, so you'll need to change that if you want to have more to work with. And then one of the things I've done as well is create some lookup tables which holds the actual tile start locations. So for example, if you are working with 64 by 64 images, then there's only 8 locations in that block in VRAM where the 64 by 64 tiles could be actually put to be able to be drawn. And obviously if you're working with 32 by 32, the same again, they can only be in certain, on certain bring this up again. You can only have them be on certain tile locations. So for the 64 by 64 images, they must be arranged in these pages in vertical steps of 8 tiles. So you can think of it as 8 times 16 to get from one block to the other. So for example, the pigeon character here, without using a lookup table, it would be a pain to actually work with the frames here. Same with the chick 64 character. So this would be the first tile here, which would be 0. And this would be tile 8. And then this would be some other high number, which would make working with them quite difficult. So to get around that, I've got code here to create lookup tables for where the images can be placed. So then you can just think of them as frames. So if I get back to this here, so when I work with the 64 by 64 sprites, the lookup table automatically calculates the top left of every starting point, and then I can refer to this as frame 0, frame 1, frame 2, frame 3, frame 4, frame 5, up to a maximum of frame 7, as you can only have a range between 0 to 7 of 64 by 64 sprites, because the 512 tile range only supports that many, as each 64 by 64 image uses 64 tiles, which is quite a lot. So one thing you could do is tile streaming when you work with these, but I don't know how well that would work out for 64 by 64 pixel images, but it would make sense to actually do that. So depending on which sizes you choose to work with, allows you to use the lookup tables to refer to the images as just frames, and then the lookup table takes care of where what the actual tile number is for that frame, which makes working with animations a lot more easy. So one thing to do when you work with the sprites, first off, is to initialize the Sprite Manager first. What that will do is it will set where our tiles are in VRAM. So if we come here, you'll see here that this is the address that we set our tiles to start at. So as I've written here, the highest number you can go to if you want to use all 512 tiles is 6,000 here, which in bytes is actually C00 or 49152 in decimal. That's the highest number in VRAM you can use and have all 512 tiles. And then I also have this define hard coded as well for 32 by 64. And then as I'm using the batch system here to easily create the sprites, so the set tile data and the set tile palette. If you've seen the other videos on or the last video, sorry, on background 1, it's the same thing for the sprites. As there are 16 color tiles, it's exactly the same things for them basically, except one thing to be aware of is their palettes actually start at byte 256 in color RAM. So the color graphics RAM is where all the palettes live. There's a maximum of 512 bytes there, so we need 256 for our sprites, as we have 8 palettes of 16 colors. So we start at 128, which is in effect 256, as whenever we use any of the DMA commands, it works in words, not bytes, as the starting address, whereas the amount you copy for the DMA is in bytes, just to make that a little bit more complicated for you. So I've got some of these commands here. We'll just straight out use the pv sneslib commands to draw stuff outright, but I find it's easier to use this batch system here. So the other sort of things I've left in here, the other commands here, there just to give you an idea of not using the batch system. So the non sort of batch calls here, these directly set stuff in OAM memory. So these are only for 16 by 16 and 32 by 32 sprites. So I'll get into the how we use the batch system to draw our sprites here. So we have our structs here. This here isn't actually used by the sprite system in here. I've left it in here as something that you can use to put some descriptive information into this struct for when you work with it outside of the sprite system, as this allows you to hold on to all of the key information about each sprite, which will make manipulating them easier. Whereas these older sprite commands here, which I've got, you have to keep plumbing in each time all of the details of the sprite to make it do stuff. Whereas using this, it holds on to it all for us. So first off, to use any of this, we have to use one of these setup functions here. So if we're working with 16 by 16 pixel sprites, we would create, or rather fill out, our sprite structure by calling one of these 16 functions here. And then you this one is like a shortened version, whereas this other one is a long version here. So you notice there's a base frame and a frame here. So the base frame is the starting location in VRAM, which frame to start at, and then the other frame can be thought of as like an offset from that, which makes animating them a lot easier and simpler. So in this demo, we're working with the 32 by 32 sprites and the 64 by 64 sprites. So we first have to set up our sprite structures here, and then to draw them, we just add them to the sprite batch, each frame, and then when we have everything that we want to draw, we then call the draw batch function, which is this part here. And then what this does here is it will hide any of the sprites which are not in the range of the batch call. And then if a sprite is visible, then we work with it. Otherwise, it will hide that sprite off screen for us. And then when so one thing to be aware of when you are using the pv/sneslib sprite commands here is the sprite ID is actually the offset in bytes where the sprite's data would live. Each sprite is made of 4 bytes, so the sprite ID is in steps of 4. So when you position the sprite, the ID has to point to that sprite number times 4. So the one of the key things that you'll need to change here when you work with this is as there's very little stored in this struct here, I wanted to keep this as minimum as possible, but at the same time provide the most functionality. So all this has here is it has a flag to say whether it's small or large. So that means if you, in this case, the 32 sprites are the small ones and the 64 by 64 sprites are the large ones. Hence, in the batch function here, if a sprite is small, then it will get what tile by looking at the image 32 lookup table. Whereas if it's a large one, then it will get the tile start location from the image lookup table 64. So if you work with, say, 16 by 16 pixel sprites, then you would want to change this to the 16 lookup table there. And then you would also, if you're using the 32 by 32 sprite setter functions with 16 by 16 sprites, then make sure you change that is small to false. So these just set up everything for us here, and then the key pvsneslib functions here is this OAM set EX. So what this does here is it sets the size of the sprite and whether it's shown or hidden. So this expects either obj large or obj small. And then this pvsneslib function here sets the attribute, the graphic offset, which is the tile number, and the sprite X and Y position, which is why I've added separate parts in here, one for update frame and the other for update XY, as there's no need to load the tile or the attribute if we haven't changed the sprite's frame. That would just waste more bandwidth that the SNES uses. So if we haven't changed the frame, then there's no need to load all of this into OAM memory. If we do have to do this, then we set the update XY flag to false, as there's no need to do it again afterwards, because you'll see that this function here only changes the X and Y position for the sprites. And then if you wanted, you could check how many are actually being drawn by checking the sprite count variable. The sprite batch variable is just a local one here. Whenever we add a sprite, the batch count is incremented. So that's pretty much all of this stuff here. You still need to maybe know some of what the pvsneslib is doing behind the scenes, and also some stuff about the how the Super Nintendo actually works with sprites. But this should be a useful bit of code here to help you manage working with them. Don't want to save anything there, just in case I break stuff. Right, now get back to the main part here. So you see I've set in here, I've created an array of twelve of these sprite structs here, and I've also created an enumeration here to allow working with the animations for the sprites to be easier, as well as the various graphics have different amounts of animation frames. So you see here you got 4 different frames for the pigeon, whereas the chicken character only had 2 frames. And then I also have some defines here which say which are the starting frames for the sprites. So the way that the frames are worked out is it literally just goes through and divides up 512 tiles into groups of either 4x4 or 8x8. So to refer to each individual frame, you can think of the VRAM tiles being split into segments of that. Again, you'll probably have to play around with that for it to make sense. So one thing that sort of decides this as well is where you load in the tile data as well. So the graphics here is loading in binary files where the tile data is stored. So if you've looked at any of the examples in the PVSNEV library there, you'll see that you create an assembly file here which basically includes binary files. So here we have the this is the actual tile data file here for the chicken, and this is its color palette. And then in the graphic define file, which I always create here, you then have to include these names here from the assembly file to be able to use them to load the bytes into VRAM. So these top parts here are all for the background tiles, and then these here are for the sprites and how many tiles each of these parts take up. I did have more sprites I actually wanted to load it in, but I didn't take into account that I'd exceeded the 512 tile limit, so I've had to leave them out, unfortunately. So you see that I've hand worked out how many tiles to actually use here, and the sort of color count for the palettes as well. When you look at the palettes here, you can see, if you look at the so this is the project here. When you look at the sort of palette files here, you'll see that they're all in bytes. So each color takes up 2 bytes. So you divide this by 2, and then that's how you know how many colors you actually have in that palette for that character. And then you ensure that when you load So this is the tile start for the sprite here, and then that's how many tiles the image is made up of. Make sure you put plenty of V-syncs in when you're loading larger blocks, as I had loads of issues trying to get these into VRAM, and also getting the palettes in as well. So the main loop here is very straightforward. Set mode 1, turn the screen on, initialize scene 2D. I'm not going to go into scene 2D in this video here. It's exactly the same as the version from the background 1 demo. If you've not seen that, then check that one out to get a full understanding of that one there. So we initialize the Sprite Manager here. We then call this to initialize the graphics and lay things out as we expect them to be. And then the key parts here are initializing our sprite array. So because of the setter functions here, it makes working with them really easy. All I wanted to do was to organize them in lines going down the screen so we could easily see them. That's all this does here. So when you initialize them, pass in the pointer to the T sprite, then you pass in the start X and Y position, then you pass in which frame you want to use, then you pass in the palette ID as laid out here in the graphic defines file. And then I'm using the ID part, the ID variable here in the sprite struct, to hold what animation character is in that sprite structure. And then if it's a 32 by 32 sprite, then the Y start position is incremented by 32 here. This is this one's for Mario, this one's for the T-Bird here. They both have the same sort of animation things here. And then exactly the same for the 64 pixel sprite parts here. Except the ID is different, and then we add 64 pixels to the vertical start position, ready for the next character, so that they're not on top of each other. And then if the Y start plus 32 is greater than 224, then we put the Y start back to 0 and add, in fact that should be 64 actually. And then just add to the next starting position. This G here is basically what type of sprite we want to have. And then moving them is pretty simple here. We just iterate over the array. Some of the things we can do here now is, because we have an ID set in here. So what this allows us to do here, if the ID of a sprite is greater than the pigeon type here, then we know it's a 32 by 32 pixel sprite. So if it's greater than 256, we set it to -32. This just allows us to wrap them horizontally. And then if it's not greater then it must be a 64 by 64 pixel one. And then this is the animation part here. So I've got a timer and a flag, which can be either true or false. of when to animate them all. So this changes the animation for them. The chicken animation is the only special one here, which is why I put the ID in. So if I open up the graphics again for that one, I will explain it again. Well, not again, sorry, I will explain what the deal with it is. So with the chicken character here, what I'll do is when we get to this frame here, I use the mirror to flip it the other way around, so we get an extra 2 frames out of it. So we in effect get 4 frames. So if we watch it again, you'll see that the hair changes there and the other leg comes up and down. So by using the mirror flag there, we can get an extra 2 frames of animation out. That's what that does there. We get the animation frame of Sprite, put it into the X, this local X variable here, add 1 to it, and then if it's a chicken character and it equals 2, then we set it back to 0 because there's only 2 frames. And then each time we toggle the mirror X in the chicken character, all the others, if a frame equals 4, then we just set it back to 0. Then put the X variable back into the frame and then call the sprite add batch function with our pointer to our sprite, and then increment the pointer to the sprite, and that's it. That's all there is. The Sprite Manager does all the heavy lifting here pretty much. So that is all I wanted to cover here. Hopefully that has or it will allow you to work with sprites a lot easier. It's definitely allowing me to work with them easier. So if you've got any questions at all about this code here, then let me know in the comment section below, and I will catch you in the next video. I will probably go into background mode 6 in the next video, and we will use 16 by 16 tile blocks for the background tiles, which require the same sort of arrangement of tiles again when working with 16 by 16 tiles. So the mode 6 offers us a high resolution mode as well. So I'll go over that in the next video. So that's it for now. Thanks for watching.